Hello, my name is Roy Simpson, and I'm a professor of mathematics at Gustavus River College in Sacramento, California. This example is a select example for integral calculus. It is typically an example found in a volume rotation or rotational solid section of integral calculus, where you rotate regions about specific lines, whether they're horizontal or vertical lines, and you have to find their volumes. And so in this case, we have a region bounded by x, y equals 1, y equals 0, x equals 1, x equals 2, and we're rotating this about the vertical line, x equals 1. Let's go ahead and graph that out really quickly because that's going to help out quite a bit. All right, we have somewhat of a really large graph done here. I sort of went overboard on this, but you could see that I do have the graph of x times y equals 1, or in other words, y equals 1 over x. That's another way of thinking about that. I only have the right-hand side of the graph because they want me to bound it by y equals 0, which is this horizontal line. It's on the x-axis. X equals 2, and x equals 1. So those are my boundaries. And then I want to rotate this about the vertical line, x equals -1. And this is kind of an important problem, and the reason why is because this, you notice, if you're going to, there's two ways to do this. First of all, if you know the shell method, that would be actually the preferred method for this problem. And if you know the washer method, and that's it, then doing this problem via the washer method requires two intervals. Okay, and so what I'm going to do, because this problem generally I assign when I have my students doing the washer method, I'm going to do it both ways. I'll do it using a washer method, and then I'll do it again using these shells. So, okay, let's go ahead and break this into two separate intervals here, because the fact is, if we're going to put a bunch of plates down and rotate by rotating about the line x equals -1, you'll see that we're going to stack these plates starting at y equals 0 and go all the way up until this red line. We'll have an outer radius of, let's see, 3 and an inner radius of 2, and we'll talk about that in a moment. And then we'll start back up on the other side of this red line. We'll have an outer radius defined by this function here, and then the inner radius defined by 2 again. So let's go ahead and do that. And maybe I should draw in here a representative slice out of this first bit. Oh, I didn't realize that my pen is at a weird color there. So let me change the color to like blue or something like that. Okay. All right, so that is a representative slice that I'm going to rotate around the line x equals -1. And as you can see, that is a dy as a thickness. Okay. And as I rotate that around, let's see, I am going to integrate from y equals 0 to y equals some value, and I'll call that value for right now, this height right here, I'll call that a. I'll figure it out in just a moment. It doesn't take too long. But when I rotate that around, I get a disk with a thickness, dy, and an area, pi r squared. Now remember, when you are figuring out that area, you have an outer radius, this big radius here, and you're cutting a hole in it. This is the size of the hole that you're cutting out to create a nice washer or board disc, or whatever you want to call it. Doesn't really matter to me. But if you watched my video on how to determine radii for rotations, this should be a pretty easy problem here. Remember, pi then times the radius squared. Well, the outer radius, let's see, is going to be, so outer radius squared minus the inner radius squared. The outer radius here is going to be the rightmost distance, which is a 2, minus the leftmost distance, or the leftmost point of the rotation, which is a -1. And then again, for the inner radius, so that's outer radius, r sub o, and now we want the inner radius here. The inner radius, the rightmost point for the inner radius here is at x equals 1 minus, And then the leftmost point for the radius, in other words, our axis of rotation, is at x equals -1. So here we go. This will equal pi times the integral from y equals 0 to a of, what is that, 3 squared, which is 9, minus 2 squared, which is 4 dy. And of course, to that, so that's just part of the volume, but we're adding something else, and maybe I should do that in a different color. I'll do that in a red color or something like that. We're adding another integral, because we're going to stack a bunch of other stuff here. So let me just go ahead and draw in that representative slice. Here it is right there. It has a thickness, again, of dy. The lowest plate that I'm going to stack in this region starts at A. The highest plate in this region ends right at this height right here, which I'll just call B for now, even though most people can easily see what that's going to be, but we'll just pretend, okay? And again, I have the same thing. It's pi times the outer radius squared minus pi times the inner radius squared. So I'll factor the pi out. Outer radius squared minus the inner radius squared. And because I'm running out of room here, I'm just going to scoot this down. I'll just leave that stuff up there blank. I'll say plus pi integral a to b here. All right, outer radius. Well, let's see. The outer radius, the rightmost edge here, is defined by y equals 1 over x. Okay? And so that's how I know that's my outer radius here. And I don't want to write y equals 1 over x because, well, that's an equation. Instead, I know it's just this x value, right? So let me write this in here. This is just some x value right there. It has some x value. And so I'll say x sub radius outer, in fact. So what I need to do is find out what x is, solve for x so that I can write it in terms of y, because remember, this is going to be a dy here. So I need to solve for x here. So I'll multiply both sides by x and divide both sides by y, and I get x equals 1 over y. So this tells me that I know my outer radius is is x here, but I know that that is actually 1 over y. And remember, subtract off your center of rotation, which is a -1 squared, and then minus your inner radius. And we've already done the inner radius, actually. It's just the same inner radius. It's just 4. It's 2 squared, which becomes 4. Okay? Let me bracket this off just because it annoys me not having that bracketed. So let's go ahead and finish this out. We need to find out what those A's and B's are. Remember, A is this height here. This is at some point x equals 2, y equals A. And this height right here is at some point x equals 1, y equals B. That should pretty much tell you how I'm going to find A and B right there, right? Just plug 2 into my function here, and I'll find out that A is 1 over 2. And then plug 1 into my function for x, and you'll find out that B is just 1. Okay, so let's go ahead and write that stuff in there. So sorry for the bad bracketing here, but my total volume is equal to pi times the integral from 0 to a, which is 1 over 2 of 5 dy, plus pi, oops, I should be doing this in my red color just so you see that this is the second half, plus pi times the integral from 1/2 to 1 of, and that's 1 over y plus 1 being squared. You can multiply that out if you want, or you can do some type of u substitution. I'm just going to multiply it out. It'll be 1 over y squared. Let's see, plus 2 over y. Plus 1 minus 4 is minus 3. And I'll put a little dy at the end. And I just did a quick pause just to make sure my math is correct, which it is. And so from this point, it's just fast integrations here. So let's go ahead and just quickly do our fast integrations. This is going to be pi times 5y, where y is being evaluated from 0 to 1/2. That 0 is going to help us out quite a bit, actually. And the stuff in red there, plus pi, let's go ahead and integrate each of these. So that's going to be a -1 over y when you evaluate that integral. This is plus 2 natural log of y. It's technically the natural log of absolute value of y, but my y values are positive, and then minus 3y, and I'm evaluating this from y equals 1/2 to y equals 1. So now I will just plug that stuff in. The first one, I get 5/2 pi. So let me go ahead and continue down here. 5/2 pi minus 0, okay, plus pi, and then here I will have some extra work, right? So I'm going to plug in a 1. I'll get a -1 plus 2 times the natural log of 1 is 0. Natural log of 1 is 0. Minus, so plus a -3, right? Because when I plug in 1, it just becomes a -3 there. And now I will start subtracting. So I'll subtract that -1 over 1/2, or in other words, I'll add 2. Subtract 2 times the natural log of 1/2. And finally subtract the negative, or in other words, add 3/2. All right, let's see what this all adds up to when we clean this up. And I'm just going to write it over to, actually, I'll scroll down. I can scroll down a little bit here. Let's see, it's 5/2 pi. Usually in calculus, there tends to be a lot of simplifications that you have to do, stuff like that. Let's see, this is a -4, plus 2 is a -2. Plus 3/2, that's a -1/2. Okay. Minus 2 natural log of 1/2. Both of these terms have pi's in common, so I'll factor out the pi. 5/2 minus 1/2 is 4/2, or in other words, 2. Minus 2 natural log of 1/2. And each of these terms have a 2 in common, so I could even write this as 2 pi times 1 minus the natural log of 1/2. And this could be simplified further. It's not that necessary to do it, but it's good practice to recall that the natural log of 1/2 is the same thing as the natural log of 2 to the -1, and you can bring that exponent outside. So that would be the same thing as negative natural log of 2. So I could actually write this as 2 pi times 1 plus the natural log of 2. Not that big of a deal, but that's just something you could do. I almost forgot to do this same problem over again using shells. So we'll go ahead and do this problem using shells. I happen to be missing my vertical line here, so let me draw in my vertical line really quickly. It looks something like that. That's all I really need. And let me go ahead and draw my the rotation's already drawn in. So if we decided to go the other way, which is actually a better way to go, but if you were to use shells for this problem, first of all, it just basically means that you decided to, instead of slice with respect to y, you're slicing these with respect to x. So you're making your slice like that. It's a little wiggle in x. And when you rotate that all the way around this vertical line here, you get a ring. And of course, if you look at the proof, I did a proof for the cylindrical shell method a while ago. So if you watch that video, you could see how this is done. But I know the volume of this ith ring is going to equal its circumference. So 2 pi times its radius here. And so the radius of this is the distance. Well, actually, technically, the radius is this total distance, right? So it's the rightmost edge. So that would be it. So that distance right there is actually an x value minus the center of rotation, which is a -1. Again, if you need to review how to find radii for rotations, then you can look at my video on that. I have a video on that as well. So, but you can all agree that the distance from here to here would be called x. So that's my rightmost point of this slice. And then you always subtract off the center of rotation, so which would be x equals -1. So anyway, that's 2 pi r. That's the circumference right there. And maybe I'll highlight that to show that that's what I'm talking about, that is my circumference. And to be very, well, I don't want to say very because I'm not really being super rigorous here, but to be a little bit more rigorous, I should say it's x sub I star, really, if I want to do that. And then, of course, that's circumference. We need a height. Well, the height for this is going to be the function evaluated at that height. So f evaluated at x sub I. I said evaluate the height. I meant evaluate the x square at that x value. So that would be the height of that rectangle. And maybe I'll highlight that just to say, okay, so now this is the height. So that's circumference times height. And then we need a width for that wiggle. And the width for that wiggle is just a delta x. Okay. And so we're going to sum up these, right? So the volume, when we rotate this around, is approximately equal to the summation I equals 1, right? We just build a Riemann sum, okay, of this junk. All right. And then we let n go to infinity via limit, and we eventually get, voila, v is equal to, or the volume is equal to, the integral from x equals 1 to 2 of 2 pi times x plus 1, right, because that's how this simplifies, times f of x, which is just 1 over x. So times 1 over x dx. Okay, and that would be the integral we're going to use. So let's go ahead and see if we could do this using any method we currently know. I'll factor out the 2 pi here, and I'll be left with an integral from 1 to 2. And then if I multiply that 1 over x against what's remaining, I get 1 plus 1 over x dx. And I can integrate both of those. The antiderivatives are in order x and plus the natural log of the absolute value, technically, of x. However, the values that our limits are positive, so I don't have to worry about the absolute values on that. Evaluate this at 2 and 1. You get 2 pi times 2 plus the natural log of 2. And then, oops, I don't mean to close off that bracket, actually. Let me erase that. I didn't mean to close that off yet. And then I will subtract this junk evaluated at 1, which is 1 minus the natural log of 1. However, the natural log of 1 is just 0. So this will turn into, beautifully, very quickly in fact, 2 pi times 1 plus the natural log of 2. Now, if you look at what we have just done, we get 2 pi times 1 plus natural log of 2. But you see how much work was required in that last example versus this one. So this is just a kind of a good justification that the washer method, the washer method is actually not always the best choice, and that sometimes the shell method, I guess is what they call it, I call it the ring method, is a better choice. And how I tell my students to make the choice is if you have the borders of your rectangle, your boundary rectangle here, your approximating rectangle, this guy, if the upper and lower borders are the same function, then definitely do the other way. So I would do dy's if that was the case. Another way to make the choice is if you have to split the integral, like we did in this example, we had to split it into 2 cases, then it might be better for you to try another method, or in this case, the shells.